Hello and welcome to another episode of TWIML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. Hey TWIML listeners, if you're a fan of our AI platforms coverage, and especially if you downloaded our first AI platforms ebook, Kubernetes for Machine Learning, Deep Learning, and AI, then today is your day. While we've been working tirelessly on TWIMLcom, I have also been working on book 2 in the series, The Definitive Guide to Machine Learning Platforms. And I am happy to say that it is finally available to download now. We created the book as a resource for ML, AI, and data science leaders and innovators to help guide their efforts in scaling and industrializing machine learning and deep learning in their organizations. In this book, we address questions such as, why invest in increasing your organization's capacity to deliver machine learning and deep learning models? What are the key barriers to delivering ML and DL models? How have organizations like Facebook, Airbnb, and LinkedIn overcome these challenges, and how can their learnings be applied to your organization? What are the state-of-the-art machine learning platforms and tools, and how can you put them to use? How can you develop an AI platform strategy to support your organization's goals? To access the definitive guide to machine learning platforms, visit twimlai.com/AI platforms. And now, on to the show. All right, everyone, I am on the line with Olivier Bachem. Olivier is a research scientist at Google Brain. Olivier, welcome to This Week in Machine Learning and AI.
Hi, Sam. Thanks for having me here.
Yeah, absolutely. I'm excited to learn more about the environment that you worked on. It's called Google Research Football. We'll dive into that. But before we do, I'd love to explore your background a little bit. You did your PhD in large-scale clustering problems. Tell us a little bit about that, how you got to that, and what you've been working on more recently.
Yes, so as you said, I did my PhD at ETH Zurich on large-scale clustering. So one thing, kind of the main question that I considered in my PhD is, how can we go and apply clustering methods such as k-means clustering to very large data sets? And I essentially worked on two major topics. One was called core sets, where the idea is you have a very large data set, but you want to run your machine learning or your clustering algorithm not on a full data set, but on a smaller set, because it might just take too long if you have billions of data points. And now core sets, they're a subset of your original data that you can find very efficiently, but that when you train on this smaller subset, you get solutions that are provably competitive as if you would have trained on the full data set. So that was one topic. And the second one was related to k-means clustering as well, where many people use an algorithm called k-means++, which is a smart way to initialize a clustering algorithm. And we worked on ways to make it much faster by, again, only looking at parts of the data, or maybe looking at it once or twice instead of multiple times.
Oh, cool. And when you talk about the core sets and having provably competitive results, is that an exercise in structuring your sample subset so that it has similar statistical properties as the larger data set?
It is, to some point. It is also about finding the data points that are very important. Turns out in many machine learning problems, but in particular in clustering, you can have billions of data points, but some data points, maybe in regions where you have very few, not a lot of data, and now you want to capture this data because it can contribute a large part to the area of your model, whereas in regions of the space where you have a lot of data, you want to take several data points and kind of group them together. So I would say that's the intuition behind the approach, but then you have to kind of do this properly in order to actually get theoretical guarantees.
Okay. It sounds like in that regard, it's somewhat related to active learning.
Well, yes and no. I think the yes part is it's about finding important points. Here, the key idea is you want to do this. Here we're doing this essentially in an unsupervised setting, right? If you're doing clustering, you don't get labels, but it's more about actually which data do you want to look at more closely. So
right,
yes,
right.
So
and I meant conceptually as opposed to in practice.
Yes.
Yeah. And so that was your PhD. What sparked your interest in doing a PhD in machine learning at all?
Yeah, so I have a bit of a non-traditional background. I did my undergrads in economics. I worked in different companies. I did a master's in quant finance, worked in some startups, did a statistics master. And yeah, during my master's in statistics, I ran across these cool algorithms where you could solve statistical problems in a very applied way. And I thought this was pretty cool. And immediately after my master's, I thought it would be cool to do a PhD in Explore.
All right, cool. And what are some of the things that you've been working on at Google Brain?
Yeah, so at Google Brain, I've done quite a lot of different projects, which I thought was really cool, but I would broadly group them into three different categories. So in the last year, I've mainly led a big effort on research into learning what's called disentangled representations.
Tell us a little bit more about that. What are disentangled representations?
Yeah, so the key idea is that in many settings in machine learning, you see a lot of high-dimensional observations, such as images or video or audio, but that these observations are not truly high-dimensional, but that they are the result of a lower-dimensional set of ground truth factors of variation. And now, when you do representation learning, you essentially want to capture or learn a function that takes such a high-dimensional observation and captures some form of information about that observation. And disentanglement or disentangled representations is one property that you might want to get when you're doing representation learning, which is you want to capture these different factors of variation in your actual representation. So one example would be if you have an image with an object in the middle, right, or somewhere on the image, you could say, for example, one of the factors of variation might be there is an object at some position, with some size, with some color, and you want to capture each of these properties independently in representation.
And can you give us a sense of, within the realm of disentangled representations, what's kind of the state of the art? What are the key tests and research?
Yeah, that's actually a pretty cool question, because this is essentially the question I asked myself about a year ago when I started working on this topic. There was a lot of papers and on this topic doing new methods, new metrics, and we started a project actually benchmarking all of these methods. It resulted in a paper called Challenging Common Assumptions in the Unsupervised Learning of Disentangled Representations. What we actually found is that when you actually train a lot of these models, and we did a large-scale study, we trained more than 10,000 such disentanglement models, we found that a lot of things happen that are quite surprising. Now, the approach that we took is we thought of it, okay, what's the approach if we are a new researcher, we get a new data set, we want to find a disentangled representation, what are the questions we actually have to answer? And as you mentioned, I guess the first question you want to answer is, which model should I use, right? What is the state-of-the-art model? Maybe a second question is, how would you select model parameters, hyperparameters to actually train your model? And thirdly, you might not just train one model, but many different models, and you might have to select the model that you actually want to use. And what we kind of found is actually very interesting, that the model that you use is not that important. It seems that all the methods that were proposed, and when you do a large-scale evaluation on many data sets with many metrics to measure disentanglement, you kind of find out that all of them can give you very good disentangled representations at the same time. So yeah, having said that, what we also found is it's very hard to select hyperparameters. Because one of the hard parts in learning disentangled representations is that when you train these models and you evaluate them, you know what the ground truth factors of variations are. But many of these methods that you actually want to use, the whole assumption, the whole point of using them is that you don't know the ground truth factors of variation. So when you do the training, you have to be kind of strict. You're not allowed to look at the labels, because that would be kind of cheating in a sense, because in the settings where you actually want to use such a model, you don't have access to these labels. So one of the hard parts is it's very hard to select good hyperparameters, because you cannot compute the disentanglement scores when you afterwards want to use it. It turns out models are quite sensitive to hyperparameters, which may not be surprising. Now, there is some hope that you can transfer hyperparameters across different data sets. But that brings me kind of to the last point, right? How do you actually select a model when you've trained many models with the same hyperparameters? What turns out there is even for a given model and a given set of hyperparameters, you can get vastly different results. You can, if you train 100 models, you're going to get some that are very well disentangled. You have some that are completely entangled. And the hard part is, without looking at the labels or without looking at the models yourself as a human, it's very hard to say which of these models you should be using. We looked at different strategies on how to do this, and maybe to illustrate with a kind of a comparison with the best thing that we could find is, even if you kind of do a smart strategy of finding good hyperparameters, you're going to beat a random model across all the models I've trained only slightly more than at a coin flip, so slightly more at 50%, something like 60%.
Well, when I hear you describe that work, I hear a couple of different things. One, I hear this like core focus on the disentanglement versus entanglement, which I'm kind of conceptualizing as like an orthogonality of these different, I don't know what you'd even call them, not models, but
I guess
spaces, representations. Yeah. Thank you. I also am in the example you gave where you've got an image and the disentangled representations are, an object and color and size and things like that. It almost starts to sound like, a holy grail of AI or AGI where you're like, there's true intelligence there. And the question that comes to mind is, to what degree are these disentangled representations generally that explainable or aligned with our intuition and how we as humans would interpret what's happening in an image, or are they just some orthogonal-ish set of representations that don't necessarily map to the way that we would interpret an image?
So I think there's maybe 2 points. So the first point, this is also one that we make in the paper, is that if you look at the task, because it's an unsupervised learning task, it is actually undefined, and we have an impossibility results, which kind of shows that no algorithm can do, this is my interpretation, no algorithm or kind of to learn disentangled representations can do so consistently for all possible world models of the world or all possible processes that generated your data. And I think that brings us kind of to the second point, right? This essentially means that you require inductive biases onto kind of the models which match the data that you want to use the models for, right? And I guess one of the hopes or the key idea why a lot of people are excited about disentangled representations is that there are such good inductive biases, right? And if you were to find a disentangled representations, and this is kind of follow-up work that we have looked into, it seems that you get quite some benefits in terms of the representations you get. We found that for non-trivial downstream tasks, when you look at tasks that require reasoning, right, abstract reasoning about the world, that you will do better if your representation is disentangled versus if you looked at, or at least we saw that this was correlated with your representation being entangled. And I think that's kind of the hope, that suddenly your algorithms that you or your models that you train, they will generalize better to stuff that you have not seen before and things like this. And I think that's why a lot of people are excited about this. But I completely agree. It matters how you define what is interpretable or not, right?
Yeah. Okay, cool. Well, for the sake of time, we'll skip some of the work you've done on generative models. That's the other thing that you spent a bunch of time on at Brain, and dive into the research that was recently published on Google Research Football. Tell us a little bit about that project and its motivation and how it came about.
Sure. So basically, I think the whole project started in late summer last year. It basically started as a kind of cool idea in our team where we had, one thing you have to see about Google Brain, at least in Zurich, where I've been, it's very collaborative. We share a lot of ideas over informal sessions, like when we go for lunch, when we go for coffee, but also in kind of within a team. And I remember we had this idea that we could use reinforcement learning to play video or kind of video games that model soccer, right? I guess a lot of people have played in the youth such video games, and we started discussing about this. What are the pros? What are the cons? And out of this, we started kind of to gain a bit of traction within the team, and we started investigating, would this be possible? Would it be feasible? And we came across this open source football game called Gameplay Football, and we thought, okay, let's see what we can do with this. And at the same time, as we wanted to do, and some people in our group were doing research on reinforcement learning, we started noticing a lot of benefits that would be had if we would build this into a fully fledged modern reinforcement learning environment. So we started, yeah.
Oh no, I was just going to ask the obvious question, which is, so what are some of those benefits?
Yeah, so I mean, the first benefit that I personally see, it's open source. So this gave us a lot of flexibility to modify the needs for a modern reinforcement learning environment. So it's primarily built for research, and that gives us a whole bunch of benefits. And the first benefit, and I mean that is also inherent to the game of football, is that it is a non-trivial problem, right? It's actually, if you look at it, it's quite hard to play. And let me maybe iterate on or kind of explain what we're actually doing here. So this is in the context of reinforcement learning, where you have to teach an agent to interact with the environment. Here, the agent has to control, and this is in the basic form of this environment, has to control the active player on one of the teams. And it has to do actions such as, okay, I'm going to walk to the right, to the left, to the top, or the bottom, and it has to pass around, shoot, as you would as a human if you were controlling a team in a football video game. And now one of the benefits is that this is actually kind of, if you think of the game of football, where you start in the middle of game with a kickoff, you have to pass around, you have to play around your opponent's defense, you have to come up with a strategy, and you have to score. That is actually a non-trivial task, and it's a challenging task. In particular, if you have different difficulties of opposing teams. That is already one of the advantages we saw. As you change the difficulty of or the strength of the opposing team, you can change the difficulty of the learning task. Similarly, you can make it much easier. You can say, well, let's say the pitch is empty and I just have to score a goal against no goalkeeper. That is even much easier, right? So one of the benefits that we saw was that it's very easy to adjust the difficulty of the game while still not being trivial, right? Mm-hmm. And that is kind of in contrast to maybe other environments that may be rather easy to solve or just very hard, computationally expensive to run stuff on. At the same time, as it's open source, we were able to build a lot of features into the game that help with doing reinforcement learning research. So one thing we could do is we can turn on and turn off stochasticity. We can make the game deterministic. And it turns out, and this is kind of still an open question research, is whether some algorithms generalize from a setting, from an environment that is deterministic to stochastic one, right?
The game is focused on controlling the player that has the ball, the players that don't have the ball, as well as the opposing team. Is there some kind of traditional, quote-unquote, game AI that's controlling those?
Yes. So maybe the one thing to keep in mind here is, so the way we structured this is we build what we call the football engine, which is a simulation of a game of football. And it supports a lot of different features. One is it supports a built-in rules-based AI, as you would probably find it in a professional video game. And at the same time, it supports a lot of features for research. And we chose that. Okay, so if you have to control all the players in your team, your task becomes much harder. We did some initial experiments, and turns out if you have to control more players, this becomes harder. So in the basic version, on what we call football benchmarks, which is in this setting, we consider the opposing players and your teammates to be part of the environment, and they play with the built-in rules-based AI. In that case, you don't control them, right? And these are basically traditional reinforcement learning problems, and we chose 3 of them as benchmark problems where people can compare different algorithms. But at the same time, the football engine that we built supports actually controlling all of the players. Or you can control all the players of one side, or we can even do a mix. I think in the paper we with this experiment where we control between 1 and 3 players. So that's completely flexible. And that's, again, one of the benefits of having a modern reinforcement learning environment that is open source.
You mentioned that you chose 3 scenarios for your benchmarking. How are those 3 scenarios distinguished?
Yes. So what we decided is, we built these football benchmarks, which we consider the current benchmarks problems in this environment. And it's essentially you play a game of 11 versus 11 football against 3 different of these rule-based opponents. And the only thing changes is the difficulty of how well these different opponents, how well the opponent plays.
Okay,
And
so some parameter to the rule-based AI that's driving them.
Yes, yeah, exactly, and kind of how quickly it reacts to you, how well it plays, as you would if you play a football game yourself. You can choose, between an easy, a medium, and a hard. Here it's essentially the same thing, but the key motivation for actually doing this is also to accommodate that different researchers may have different computational budgets. So it turns out if we are running currently with the algorithms that we tried, and we found that if you run on medium and hard problems, it becomes quickly very challenging, and you might have to go to distributed implementations of different algorithms. You need quite a lot of computational resources, but at the same time, you also want to provide benchmark problems where you could go with a single machine, maybe a single GPU, and you could actually test your ideas and compare against other algorithms, right?
Mm-hmm. Mm-hmm.
And I guess, there's different areas, right, of reinforcement learning, such as learning with few samples. I think this is one of a very hard problem in reinforcement learning, but it's also very relevant. And even if you don't have a lot of computational resources, you can still go and benefit from this environment.
Okay.
Yeah, I mean, one thing also, we also added what we call the Football Academy. And this is essentially, as I said before, like having that flexible game engine allows us to really kind of change what is happening on the pitch. And one inspiration we took when football teams train, right, they might do some drills, and we can actually model this, right? We can say, well, let's not have 11 versus 11 players. Maybe let's play 3 versus 2 counterattack. And we defined a set of different such academy scenarios, as we call them. They start with very easy ones where you're close to the goal. There is no goalkeeper, and you just have to score. So you have to eventually learn how to walk into the goal or how to kick the ball into the goal, to more difficult problems where you play with 11 players versus a goalkeeper, or as I said before, counterattack scenarios that kind of accommodate very different game situations, but also which come with very different difficulty levels. And maybe the key thing here is the easy ones, right, where you just have to scores. On these, you can, like, if you're on a single machine, you can get results with current algorithms within minutes, or let's say 10, 20 minutes, instead of having to wait a full day and block a full machine before you can kind of tweak your algorithm or check your implementation. So I think that's also like one of the key advantages of the environment. You can go and start with very simple cases and kind of see where does it break without always having to wait a very long time in between. You can also define your own scenarios. So there is a lot of flexibility, and I'm pretty excited about it. Yeah.
I suspect this is going to be well beyond the scope of what you have looked at so far, certainly at this paper, but have you explored kind of the idea of transfer learning or curriculum learning, like training an agent on these academy scenarios and how that might impact performance on the game as a whole?
Yes. So in the last few months, we've been very busy pushing out this environment and, fixing bugs and running the experiments we had in this paper. It has certainly been on our mind, and one of the motivations actually for the Football Academy was to enable curriculum learning. we didn't include results here. In the paper, we include benchmark results for the different academy scenarios to kind of show how hard they are, and kind of this role, as I mentioned before, where you have a variety of tasks which are of different difficulties, but you can use this to go and build your own curriculum, right? And you can see, does this fare better at actually playing the 11 versus 11 game than if I just start to play the 11 versus 11 game?
So you've talked about some of the benefits of your environment in terms of it being open source and some of the features that you built in. But I'm curious, taking a step back, are there, any thoughts in terms of, some unique properties of football/soccer as a task for reinforcement learning agents? There are a ton of RL simulation types of environments, everything from kind of the tower challenges kind of things to very, domain specific, to the more general, teach some agent to walk kind of environment. Plus Atari games, right? Why is football potentially, interesting or more interesting than some of these many other tasks?
Yes, so I think the key benefit of football is twofold. Now, the first one is, I think the task as we have it now is challenging even for modern reinforcement learning algorithms. Now, if you look at, for example, the hard scenario, even playing against a fixed rules-based AI with a general learning algorithm, we need to run a lot of several hundred millions of steps in a distributed setting where we have several hundred machines actually running this game, right? So I think having a challenging task is very important. Now, when you do research here, every research is kind of free how to choose the approach, but one of the hopes is that if you take a general kind of learning algorithm, which is not specific to football, that it would also transfer to other settings, right? Now, in terms of how does it compare to different environments, I think the key part, what I mentioned before, is that we can adjust the difficulty. This allows you to do research on a variety of different difficulty levels. I think that's different to prior environments, such as Atari, which I guess now people would consider rather on the easy side. On the other hand, there has been reinforcement learning research on other video games, such as StarCraft 2 or Dota 2, and which is rather on the computationally expensive side. Here you get kind of everything, right? At the same time, it's also open source, so you don't need access to a potentially a closed source binary. The other part, and I think that's also one thing we are very excited about, there is essentially two extensions that we put into the environment, which is it allows to play multiplayer in a sense that football is inherently a multiplayer game where you play against an opponent, which brings a completely new dynamic when you have somebody else acting in the same environment but with adversarial goals to you. Similarly, the environment supports actual research into multi-agents, where you could think of every single player has to make their own decision on what he's going to do. And now you have two teams, right? And they have to start cooperating. Players within a team have to start cooperating with each other to play against somebody else. And I think this is just very broad range of topics that you can investigate. Similarly, we built into the engine that you can go and train on different representations or different types of observations. So you can either go and train about pixels, which may be computationally expensive, or we can go at other representations of the observations, such as the actual positions of the players, right? Not all the data is images, and you can do something which you cannot do in other environments.
Mm-hmm. So the representations can be, in addition to just looking at the images, you can get the kind of more inherent state. What about on the control side? What are the options that you have on control of the player with the ball?
Yeah, so there has been other reinforcement learning environments, which are also doing football. This is DeepMind Soccer and RoboCup, the 3D simulation. Now, these are more on the side of doing continuous control, where it's really about low-level control of the either the robot in RoboCup or the simulated robot in RoboCup that you control, or essentially a kind of players in this DM soccer, where you really you have to specify how much do I turn, how much do I go forward and back, which is much more focused on low-level control. Here, the idea is more you want to learn how to do these more high-level control, right? Like things like strategy, tactics become much more important. Here you control, as you would with a gamepad. Essentially, you can move right, left, top, bottom. You can sprint, you can pass, you can try to press when you're in defense, and so on. But again, the environment is open source, so this can be modified, right?
So it sounds like the way that you control the character is one of the key distinction between this environment and some of the others that are out there for this game. Are there other distinctions?
Yeah, I think that is one of them. It's in particular with regards to the other environments that do football. That is, for me, the key difference. I think to the other ones, the actual tasks that you're doing, the fact that you can go from different types of observations, that you can adjust the difficulty, that it's open source. These are all differences. I think one of the points here is also, I think there's also in reinforcement learning always a certain investment required in going and using an environment. And what I like here is in one environment, you can essentially do a lot of different types of research.
Maybe share a little bit about where your group goes from here. This has been published out on GitHub. When did it go live? When was the environment published and the paper published?
Yeah, so we put this kind of right. We finished a sprint just before ICML, where we first pushed this to GitHub with an accompanying paper which describes the environment. Since then, we had a demonstration at ICML at the Google booth where we showed this to people. We got a lot of feedback. We've worked on the environment actively since then. We added a lot of cool features that I'm excited about. This multiplayer feature where you can do self-play, for example. We've added multi-agent support. We've done optimizations to the game engine. It runs now 3x faster. And we've just recently updated the paper and put it on archive with more experiments where we investigate kind of the first experiments into 3 different research directions, which we think are very promising in this environment. One of them is what happens if you do self-play. Second is what happens if you do this multi-agent setting where you control more players. And third one is what happens if you use different representations of the actual environment or the observations that the agent interacts with.
And so from this point, does your group continue to work on kind of the environment itself, or do you start to branch off into doing more experimentation work in the environment? Where do you see your work going with this?
Yes, so we're definitely, I think there is, as you said, 2 things that we want to do. The first thing is we want to make sure this is a useful research or reinforcement learning environment. So we're definitely going to continue adding features, make it easier to use the environment. I think the potential that it has, especially with the multiplayer component or where you have to compete against other agents. We are definitely looking into options how to make this more accessible. At the same time, we are also super excited to do research on this environment. Yes. And also, I think one thing that we should highlight here, this has been a big team effort in the team here. So it has been over 10 people that have worked actively on this project, right? And now I think it's also maybe a time where different people are going to explore different things in this environment.
And so, Olivier, maybe what are 3 things that you personally learned in working on this project?
Yeah, so For me, this has been quite a cool experience. I didn't really do reinforcement learning research before I came to this project. So for me, I learned a ton about all the different environments that are out there, about different algorithms. And I also learned, and this is kind of a funny anecdote, that even now, these algorithms that we have, they're very good at exploiting kind of loopholes in the game engine. And like one example that people in our team found, and I thought this was pretty funny, is if you have 11 players playing football and trying to score against a single goalkeeper, what is kind of the best strategy to do? And it turns out in the version that the game that we had at that time, what the agent learned is it would go take the ball, kick it outside of the playing field, so that the goalkeeper has to go and do a throw in where he doesn't have any teammates, so he's going to throw it somewhere where the other players have it, and now the players will score. And I think that I think it was a pretty cool example that we found.
How long did it take the agent to figure that out?
I don't remember the details, but it's kind of like once it found this, it's a super smart strategy, right? And it's really exploiting kind of a loophole. We had a similar one where essentially when you train these agents in the beginning, the opposing team scores a lot and you're kind of learning not to admit any goals, right? And one thing I learned is, for example, that once the opposing player, for example, kicks the ball besides the goal, your goalkeeper, when he's doing the kickoff, he can just wait indefinitely because the engine didn't include any mechanism to prohibit that. And that is a good way to minimize, the opponent scoring goals if the game doesn't continue. And I think these things are super funny. And I think it also highlights one of the things which we didn't really talk about yet, but which is that like doing research in this football environment also makes that research to some degree more accessible, right? A lot of people, they care about football, they like watching football, it's very intuitive, and that's why we hope that actually having a football environment also helps with actually people, maybe demystifying a bit what is happening in this research, so that people can see, this is a random agent, it's doing this, right? And then suddenly it starts learning how not to admit goals, and then you see how it learns to score. I think people can very much identify with it. Students that are doing master programs that want to learn about reinforcement learning, it's super cool. You can go with the environment, learn how to pass or kind of score against an empty goal, then 2 versus 1, and so on. So I think that's maybe one of the benefits that we didn't really talk about, which is that it is a very accessible environment, right? You don't like a lot of people know about football.
Mm-hmm. And of course, you just recently published this, but are you aware of any efforts or plans to incorporate this into kind of learning curricula?
So deep learning and reinforcement learning is a very fast-moving field. So we chose the approach of releasing the environment and putting online the paper. So this has not been published yet. It's on the web. Everybody can use it, but we're definitely trying to publish this, but it has not been published yet.
Got it.
And as to the second question, for curriculum learning, we did some very initial experiments.
Just to be clear, I'm more talking about, do you see application? Well, you spoke to seeing applications of this environment in the education of humans and growing their own knowledge of reinforcement learning. And I was just curious if you were aware of any plans to formalize that and maybe build it into, some online course or some school-based course to teach students about reinforcement learning using this metaphor that they're very familiar with.
So I'm not aware of this, but I definitely hope that this happens. We've seen quite a lot of positive feedbacks on things like Twitter, where people got very excited about that. So I definitely hope that helps people access research. Again, also, given that it's open source, it's very easy to use or to get started. If people are interested in, even if your listeners are interested in, we go to our GitHub page, github.com, Google/research/football. It's very easy to get started. You can install the environment. There is examples which show you how to train a basic agent. So I'm all for making it as accessible as possible.
And you talked about the agents that you've played with finding these kind of corner cases to exploit the environment. How do you address that? It strikes me that, in some cases, the solution to that is maybe putting in more constraints that are like the human game of football or better modeling that environment. In other cases, you might need to do something that doesn't make sense in the context of the actual sport. And it's kind of creates this own, this, unique computer football sport. Does that comment resonate at all? And how have you addressed those kinds of corner case issues?
Yeah, so we ran a lot of experiments, and as you said, it is actually pretty hard to build a good reinforcement learning environment. Now, I think now we are pretty confident that it works pretty well, but that doesn't exclude that, you go come with a new learning algorithm, it's really good, it finds another corner case. I think we then have to kind of address this on a case-by-case basis. I think it also boils kind of back to the underlying motivation, right? I think the motivation is not necessarily, playing this like playing as well as possible in this environment as a primary goal, but the goal is to do research, right? And if there are things that hinder research in this environment, then I guess we have to change it. On the other hand, I think there's also, and I think this is the general feeling in our team, there's a benefit to having stability on the environment side so that research and results stay comparable across different papers. So we definitely don't want to change the environment too often, but if there is very obvious failure cases, right, which you can never exclude, then we might have to do this, right?
It sounds like then that for the most part, these exploitable corner cases, you've kind of considered them as bugs as opposed to, inherent qualities of the game that you're trying to model. Does that make sense?
Yes, I think so. I think, the example of the goalkeeper having to go doing the throw in, that really defeats the purpose of these scenarios we've defined, right?
Yeah.
Similarly, the example that I gave where the goalie doesn't kick it away, right? Like if you do this in a real game, you would get a delay of game penalty, right? Mm-hmm. Or you'd be at least something would happen. I think that really shows, okay, maybe this was really a bug in the implementation, right? I think, on the other hand, also boils back to, right, whenever you're building an environment like this, right, you have to take some choices. We've done this with a kind of best faith effort, and we think now it is kind of ready to be used for research.
Well, Olivier, thanks so much for taking the time to share this project with us.
Yeah, thanks for having me here.
All right, everyone, that's our show for today. If you like what you've heard, please do us a favor and tell your friends about the show. And if you haven't already hit that subscribe button yourself, make sure you do so you don't miss any of the great episodes we've got in store for you. As always, thanks so much for listening, and catch you next time.